And say we have a logic expression that says F1 equals A, B plus C naught, D. Okay, we have this logic expression, and what this logic expression, it's not simplified. And what Boolean algebra is just simplifying logic expressions. And we use that by using Boolean theorems. And you don't need to memorize these. I'm going to give you this sheet of paper. All right? And we're going to use these different theorems to simplify this. Okay? So let's just jump right into it. All right? So what we need to look for are these scenarios. So x multiplied by 0 is 0. All right, x and naught is naught. Okay, x and 1 is x. X and x is x. X and x naught is 0. They kind of cancel each other out. All right, x plus 0 is x. X and 0. Addition is and, or, I'm sorry, is or. All right, x or 0 is x. X or 1 is 1. X or x is x. X or not x is 1. And double naught. Okay? Double naught. If you not a naught, it's x because you're inverting an already inverted signal. Okay? So you're inverting it back to x. All right. So let's look to see what we can use in here. And let's just look at the first term first. A and B. All right, so A and A. We look over here, we search for X and X is X, okay? So we have A and B, and A, X and X equals X. So A and A is what? A and A is just A. All right, cool. And we use theorem number 4 there. Okay, or I'm sorry, that's theorem number 3. Okay, theorem number 3 there, x and x is x. Okay, plus, all right, what's c and c naught? Okay, that'd be x and x naught. X and x naught equals 0, so we could put a 0 there, 0D. All right, and that was theorem number, what was that? Theorem number 4. Okay, theorem number 4. And okay, can we simplify it more? Yeah, I think we can, because there's a theorem that says, x and 0 equals 0. X and 0 equals 0. Where do we see that scenario here? We have a variable and 0 equals 0. Right here, we have 0 and D. D and 0 equals 0. And that was theorem number 1. All right, and then we can't reduce AB anymore. Okay, and do we really need to write the 0 anymore? No, not really, because it's a 0, so we can just get rid of it. We can say AB, F1 equals AB. So we're just using these Boolean theorems as tools to simplify these logic expressions. Okay, let's look at another one. All right, we have all kinds of other laws in Boolean algebra. We have commutative laws, associative laws, distributive laws, consensus theorems, okay? And they're all going to be listed on this sheet of paper. And all these things are laws that we've learned in past mathematics courses, all right? So x multiplied by y, x and y equals y and x, okay? X or y equals y or x, all right? Distribute, or associative, distributive laws down here. Associative laws, so x multiplied by yz is xy multiplied by z, okay? X or the quantity of y plus z equals x, or the quantity of x plus y or z, all right? X multiplied the quantity of y plus z equals xy, xz, all right, and so on and so forth. Okay, now down here we have our consensus laws, and the consensus laws are just a little bit different, okay? And what we use these for, they're really handy in simplifying things pretty easily. All right, and we're going to use these laws pretty extensively, the Demorgan's laws and consensus laws. All right, and what we're going to do is we're going to look for these scenarios in logic expressions, and we're going to substitute the output in. So we have an input, all right, we have an input here, and we're going to look for the input, and then we're going to get an output coming out into the next line of the logic expression. Okay, so think of it in terms of inputs and outputs. So this is what's coming in, and this is what's going out. Okay, so x plus not x, y equals x plus y. Okay, because the not is really it just goes away. All right, so not x plus xy is not x plus y. Okay, and x plus x naught y naught is x y naught. All right, x naught plus x y naught equals x naught y naught. All right, so the outliers are kind of going away in this. Then Demorgan's theorem basically says that if we have x naught y naught, it's going to equal x naught or y naught. It's going to come out the same. And we could draw this out in logic gates if we wanted to, but we're not, at least not right now. So x naught or y naught is going to come out x and y. All right? So all we're doing, and all you need to think right now, is substitution. Substitution is key. Okay? Substitution is all we're thinking right now. So we're going to look for these scenarios in logic expressions, and we're going to substitute things in. Now let's do one more example. Okay, and this example is a pretty extensive example. All right, and we have F3 equals R naught T, or the quantity of R S naught multiplied by the quantity of R naught T. Okay, so we have all of our theorems over here, okay, and everything that we need to look through. All right, and you have this piece of paper right in front of you. At least you should while you're watching this video. So you can look through it with me. All right, so let's look through what we can do here. Okay, we have two quantities that are together, all right, that we can reduce or do something to. And let's look for something where two quantities together, oh, right here, distributive laws. All right, so we have first term of the first quantity, first term of the second quantity here. We have the first term of the first quantity, second quantity. You know how to distribute. So let's distribute this out. So we can say R naught T, or R naught and T, or, okay, R naught plus RT plus S naught R naught plus S naught T. Okay. All right. So we've got all that. And that was theorem number 15 on our theorem sheet. Okay. It's good to keep track that I know that's the theorem you use. So do this. When you're actually doing the work, do this. Say, I use theorem number 15, just so I know. All right. And then what can we do next? All right. We have right here, this is a red flag. Okay, we have R and R naught. What's R and R naught? They kind of cancel each other out. R and R naught would be 0, okay, because of theorem number 4. X naught and X and X naught equals 0. Okay, so we use theorem number 4 here. All right, R naught T plus 0, or RT, or S naught R naught, or ST, S naught T. Okay, can we go any further? Well, yeah, we can. All right, so if we look at theorem number 5, all right, theorem number 5, okay, what's 0, okay? X and 0, theorem number 5. I'm on theorem number 1. X or 0 equals X, okay? X or 0 equals X. So we have X or 0 equals X. Think of this as just an X. X or 0 equals X, okay? X or 0 equals X, we can just simplify that down to be RT or R not T or RT or S naught R naught or S naught T. And we use theorem number 5 to do that, okay, because X plus X or 0 equals X, okay? Now, we can definitely go farther, all right? We can factor out something out of this term, okay? So we're going to use the distributive law in reverse, okay? So we want this, but we have terms like this, okay? So what term can we take out of this factor out of this logic expression? How about a t, okay? Because this one has a t, this one has a t, and this one has a t. All right, this one we're going to leave alone, and so we can say t multiplied by, now what terms have a t in them? T and r naught or r or s naught. And we're going to close that, and then we're going to say or s naught r. Okay, and we use theorem number 14 for that. Okay, 14 for that because 14 is x multiplied by a quantity of other inputs. All right, so we have t multiplied by a quantity of other inputs. Okay, and yeah, we can go even farther than that because we can break stuff down inside of this quantity. All right, so we have r or r naught, r or r naught, or s naught, r or r naught plus s or s naught. Okay, so what we can do is we can say, oh well, look through our theorems, and x or x naught is 1. X or x naught is 1. R or r naught is what? 1. So we can break it down even farther and say t multiplied by the quantity of 1 or s naught plus s naught r. Okay? So what this really says is t and 1 or s naught or s naught r. Okay? And can we go, what theorem did we use for that? We used theorem number 8. Okay, let's look at what's in the quantity still. We can still simplify what's in the quantity. We have 1 plus an x, okay? 1 plus s naught, 1 plus a input, okay? So 1 plus an input is 1 plus an input is theorem number 6, and that's just 1. So we can say t and 1 or s naught r. And we use theorem number 6 for that. So number 6. And s naught r, we really can't do anything with, but t and 1, an input and 1. An input and 1, that's theorem number 2, is the input. Okay, so the input and 1 is just the input, t plus s naught r, all right, t or s naught r. We use theorem number 2 for that, and we're done. That's it. That's as far as it can go, all right? And usually what you would do is you would search and make sure you can't break anything down any farther, but this, I know this is as far as we can go, all right? So that is what we're doing. We're just using the tools on this theorem and equation sheet, okay, to simplify logic expressions. All right, and you have this